Hello students, welcome to this lecture on recursive least squares adaptive filter. Let us recall the LS estimation problem for signal estimation by adaptive filter is, this is the problem: minimize the weighted sum square error given by summation lambda to the power n minus k into dk minus y transpose k into hn whole square, k going from 0 to n with respect to the filter parameter hn. So, we have to minimize this weighted sum square error with respect to the filter parameters, and here dk is the desired signal and yk is the input signal. The minimization gives the normal equation for the LS estimation, and this is given by this equation: summation lambda to the power n minus k yk vector into yk transpose k going from 0 to n into hn vector is equal to summation lambda to the power n minus k into dk into yk vector k going from 0 to n, and this we write in usual notation, that is ry hat n for this into hn r dy hat for this expression. So, is equal to r dy hat n. This solution, this is the normal equation, and we can solve it by matrix inversion. Hn is given by ry hat inverse n into small r dy hat n. So, this is the inverse of the estimated autocorrelation function, and this is the estimated cross correlation function. The RLS algorithm finds the above inverse, this inverse recursively. Let us recall the RLS algorithm. It is initialize this P matrix, P of minus 1 is equal to 1 by delta into identity matrix, where delta is a small positive number, and filter coefficients are initialized 0. We have to choose a proper value of lambda around 0.95, 0.98, 0.99, like that. Now, for n is equal to 1 onward, we will carry out these computations. First, get dn yn, get dn and yn, this is the desired signal and this is the input vector. Compute the filter output d hat n is equal to, that is previous filter estimate into yn vector. Then we compute en is equal to dn minus d hat n. D hat n we have computed, dn is here. So, we have to find out the error. Next step is to calculate the gain vector kn. Kn is given by p n minus 1 into yn, that is the current data, P matrix into current data divided by lambda plus y transpose n into p n minus 1 into yn. So, this is the current data and past estimate of the P matrix. Then we will update the filter parameters by this relationship: hn is equal to hn minus 1 plus kn times en. So, kn is the gain vector. Once we have calculated the filter coefficient, we have to update the P matrix, and this is given by Pn is equal to 1 by lambda times Pn minus 1 minus Kn into Yn transpose into Pn minus 1. So, this is the update equation for the inverse of the autocorrelation matrix. This lecture will discuss the properties of the RLS filter and illustrate two applications of RLS adaptive filters. Let us first see the relation of the RLS adaptive filter with winner filter. we have the optimality condition for RLS filters given by the normal equation, that is RY hat n matrix multiplied by Hn vector is equal to cross correlation vector, that is R dy hat n. So, where Ry hat n is given by this relationship, weighted sum of Yk into Yk transpose. Yk into Yk transpose is a matrix. So, this matrix for different instant k are summed up. Similarly, R dy hat n is equal to summation lambda to the power n minus k into dk into yk, k going from 0 to n. Here dk into yk is a vector, and this vector summed up for different values of k, and we get this estimate. Under stationarity condition, we take lambda is equal to 1, dividing by n plus 1 this expression. If we divide this expression by n plus 1, we get Ry hat n divided by n plus 1 is equal to summation Yk into Yk transpose, k going from 0 to n divided by n plus 1. So, this is the expression for Ry hat n divided by n plus 1. Now, if we consider the elements of Ry hat n by n plus 1, we see that each is an estimator for the autocorrelation of specific leg. So, for example, the first element of this summation will be yk into yk. This will be the first element, summation k going from 0 to n and then divided by n plus 1. So, this will be the estimate for the variance. So, this will be sigma y square hat. So, that way all the elements of this Ry hat matrix divided by n plus 1 will be the corresponding autocorrelation function at specific leg. So, this is important observation. Under stationarity assumption, this matrix divided by n plus 1 as limit Ry hat n divided by n plus 1 as n tends to infinity will be Ry. This is because the sample autocorrelation function is a consistent estimator of the true autocorrelation function under stationarity assumption. Similarly, limit of R dy hat n divided by n plus 1 as n tends to infinity will be the cross correlation vector R dy. Hence, as n tends to infinity, optimality condition can be written as Ry matrix into H is equal to R dy vector. That is, this is the Wiener-Hoff equation for the Wiener filter. Thus, if the data is stationary, the algorithm will converge to the Wiener solution. So, this is important observation. Next, we will see dependence on the initial values of P matrix, because we initialize P matrix here. P of minus 1 is equal to 1 by delta into identity matrix, where delta is a small positive number. Consider the recursive relation, that is Ry hat n is equal to lambda times Ry hat n minus 1 plus yn into yn transpose, corresponding to the initialization Ry hat inverse at minus 1 is equal to delta I, that is P of minus 1 is equal to delta I. This is P of minus 1 is equal to delta into identity matrix. So, corresponding to Ry hat inverse at point minus 1 is equal to delta I, we have, so inverse is delta I, so R y hat at point minus 1 will be I by delta. With this initial condition, the matrix difference equation, that is the difference equation corresponding to the recursive estimation of autocorrelation function. So, the matrix differential equation has the solution like this: R tilde n, because we are assuming this initial condition, is equal to lambda to the power n plus 1 into R y hat minus 1. So, this is the initial condition plus summation lambda to the power n minus k into yk transpose k going from 0 to n. So, this we can write like lambda to the power n plus 1 into R y hat minus 1 plus, this is by definition R y hat n. So, this will give us lambda to the power n plus 1 into I by delta into R y hat n. So, because of this initialization, we have an additional factor like this. Now, our autocorrelation at different instant will be given by this expression lambda to the power n plus 1 into I by delta plus actual estimation R y hat n. Hence, the optimality condition of normal equation is modified to this, that is lambda to the power n plus 1 into I by delta plus R y hat n into H tilde n must be equal to R dy hat n. So, this is the modification in the left hand side because of the initialization of the P matrix as delta into I. So, this is the modified normal equation, where H tilde n is the modified solution due to the assumed initial value of the P matrix. Now, taking the inverse, so this we get pre-multiplying by R y inverse n. So, we are pre-multiplying here. So, R y hat inverse n, here we are pre-multiplying, this will be now identity. So, H tilde n will be there, and here if we multiply it by R y hat inverse n, then we will get H n. So, that way this relationship we get. Now, if we take lambda less than 1, lambda is less than 1, then the bias term, this is the bias term in the left hand side of the above equation will be eventually die down. As n tends to infinity, this term will become 0 because lambda to the power n plus 1 will become 0 as n tends to infinity. And we will get H tilde n is equal to H n. So, therefore, because of this initialization we have taken, that is R y hat inverse at minus 1 is equal to delta I. So, this will not affect the solution. So, ultimately we will get H tilde n equal to H n. Unlike the LMS filter, the convergence is less sensitive to eigenvalue spread. We will note one more thing, that unlike the LMS filter, the convergence is less sensitive to eigenvalue spread. This can be shown, but we take this as a result. This is a remarkable feature of the RLS algorithm. So, we also note this. We note, unlike the LMS filter, the convergence is less sensitive to eigenvalue spreads, and this is one of the remarkable property of RLS algorithm. Next, we will consider tracking of non-stationarity. If lambda is small, lambda to the power n minus 1 will be approximately equal to 0 for I mass less than n. Suppose for smaller value of I compared to n, lambda to the power n minus 1 will be approximately 0. This implies that the filter is based on the most recent values only, because we are weighting every error by lambda to the power n minus I. Therefore, the filter will be based on the most recent values. This also qualitatively explains that the filter can track non-stationarity in data. So, this is one important factor, that because of this forgetting factor, RLS filter can track non-stationarity in data. The rapid rate of convergence of the algorithm ensures that the algorithm tracks rapidly varying data. This is another observation. The rapid rate of convergence of the algorithm ensures that the algorithm tracks rapidly varying data. Thus, the RLS adaptive filter is preferred when the input data have rapid variations. So, under this situation where input data have rapid variations, RLS adaptive filters are preferred. Next, let us see the computational complexity of RLS filter. Several matrix multiplications result in a complexity proportional to m square. This is the complexity, it is proportional to m square because of different matrix multiplications involved in the algorithm. This complexity is quite high if the filter tap length is high, because it is m square. So, this complexity is high. So, we have to go for faster versions of RLS algorithms. There are several faster RLS algorithms like the lattice RLS adaptive filter. Another disadvantage of the RLS algorithm is its sensitivity to round up errors. So, because of the recursive nature of estimation, the errors accumulate during recursions and may lead to instability of the algorithm. So, this is one drawback, and another drawback is the computational complexity. Thus, we have seen that RLS adaptive filter has a better convergence characteristics compared to LMS filters, but it has higher computational complexity. Let us consider one example: adaptive linear prediction. Consider the AR2 signal. This is an AR2 signal. Yn is equal to 1.72 Yn minus 1 minus 0.81 Yn minus 2 plus Wn, where Wn is a zero mean unity variance white noise process. This is a autoregressive process of order 2, and the second order linear predictor for this signal is given by this y hat n is equal to h1 into yn minus 1 minus h2 into yn minus 2. So, this is the linear predictor, and under optimality condition we can show that this linear predictor is equal to same as this AR process terms. So, that way y hat n is equal to 1.72 yn minus 0.81 into yn minus 2. Here the LP coefficients are to be computed adaptively. And now for adaptive filtering, this is my yn. Now for linear prediction, we have to consider the delayed version of the signal. Suppose this is delay and this is the delayed version of the signal, and this delayed version of the signal is passed through the two-tap FIR filter for linear prediction. So, we will get, suppose this is d hat n. Now, this yn is the desired signal here. So, this is the desired signal, dn is equal to yn. and this desired signal will be compared with d hat n, and the error En will be computed. Now we have the adaptive filter algorithm, that is RLS algorithm here, RLS algorithm. So this error will be passed here, and this will be passed to here also, and the filter coefficients will be updated, and the filter coefficients, these are the filter coefficients. So these filter coefficients will be used to filter this signal, delayed version of the signal, to get d hat n. So this is the implementation of the second order linear prediction. This is a two-step filter, and this is the delayed version, so that it will compute d hat n is equal to some h1 times y n minus 1 plus h2 times y n minus 2. So we use RLS algorithm, and we have to initialize lambda. Lambda we use 0.98, and similarly the P matrix is initialized. Suppose P of minus 1 is equal to delta. Delta we can take suppose 0.01 into identity matrix. This is a 2 by 2 identity matrix. So with this, if we run the RLS algorithm, then the solution will look like this. So this is the desired signal, is this blue is the desired signal, and red is the prediction using RLS filter of lambda is equal to 0.98. And we see that initially there is mismatch, but as n increases, the predicted value and the desired value of the signal are very close. They are almost matching. We will consider second example, example 2. This is the example 2, system identification. You are given a 6-length FIR system with unknown parameters. We know it is an FIR system, but parameters are unknown. Identify them. We have to identify them. Suppose this system is given by this. We are considering a 6-step FIR system. Hz is given by minus 0.0078 plus 0.064 into z to the power minus 1 plus 0.4433 into z to the power minus 2 plus 0.4433 into z to the power minus 3 plus 0.064 into z to the power minus 4 minus 0.0078 into z to the power minus 5. This is the transfer function of the unknown system which we want to identify. So this adaptive system is like this. This is the, we have to send a broadband signal, usually a white noise signal yn is input to both the system and the adaptive filter. Here we consider a 6-length adaptive filter. This is the 6-length FIR system, and a white noise yn is input to both. Now the output of the FIR system is dn. This is the desired signal, and we want to mimic this system by this adaptive filter, and this adaptive filter output is d hat n, and this dn and d hat n are compared, and the en will be passing through the adaptive algorithm. Suppose this is the adaptive algorithm, adaptive algorithm. So, this error is sent here, and similarly yn will be sent here. So, the adaptive filter will be operating, and then this error, this filter coefficient whatever are estimated, that is fed here. So, these filter coefficients are used to filter this signal, and if there is error, this error is again used to update the filter parameters. So, this is the system identification system we are using. Here this 6 length adaptive filter will model the 6 length FIR system. Again we apply the RLS algorithm here, RLS, and we take lambda is equal to 0.98. So, these are the simulation result. Original system is like this. This is the transfer function of the original system, and the estimated transfer function using the RLS algorithm we get this h at z is equal to minus 0.078. This is same here also. This is a symmetric filter because of the linear phase. So, here also minus 0.0078, this is same. Similarly, this is 0.064, here 0.0645, only difference in the 4th decimal place. Similarly, these are equal, this also equal. So, that way this RLS filter identify the given system. We also examine the convergence characteristics. This is the error, absolute error after each iteration, and we see that in the case of LMS algorithm with mu is equal to 0.2, this blue values are the error values, and these are the error values when RLS with lambda is equal to 0.2 is used. So, this is RLS. So, we see that this error is gradually decreasing at a very fast rate. So, this is one important observation in the case of RLS filter. Let us summarize the lecture. The RLS adaptive filter has several attractive properties. Under stationarity of the data, the RLS solution converges to the winner solution. This is very important. Unlike the LMS filter, the convergence is less sensitive to eigenvalue spread. This is a remarkable feature of the RLS algorithm. Unlike the LMS algorithm, RLS algorithm is computationally complex. This is the disadvantage of the RLS filters. Several matrix multiplications result in a complexity proportional to m square. So, this algorithm may also suffer instability because of the accumulation of round of error during recursion. In the next lecture, we will discuss one more important filtering technique, that is known as the Kalman filter. Thank you.